Hello again. The SHA-64 language has now two-dimensional byte arrays. Let's have a look. Let's open an example. In this example, we animate a bouncing ball on the screen. The variable random points to a jiffy tick register that is automatically incremented by the Commodore 64. The screen is defined as a two-dimensional byte array located in the memory address 400 in hexadecimal. The variables row and col define the row and column position of the bouncing ball on the screen. Then the variables rmove and cmove indicate the direction of the ball with respect to the current row and column position. The variables rbounce and cbounce indicate if the ball is to bounce vertically or horizontally. Lastly, the delay variable is used to implement a busy loop that slows down the animation. As for the functions, the wait function implements the busy loop. The checkBounce function evaluates if a vertical or a horizontal bounce is to take place. Lastly, the move function animates a single motion step for the bouncing ball. The animation step first removes the ball from the screen. It then moves the ball by changing the row and column position. The move function contains also a random sidestep. Each time the ball is in the bottom row, it may take a sidestep to left or to right. It may also stay on the current path. The random sidestep ensures that the path of the bouncing ball will eventually change over time. In this way, the ball does not get stuck to one repeating path. Then, before painting the ball, the function stores the character value from the screen. In this way, the stored character value can be used to remove the ball from the screen in the next iteration. Lastly, it paints the ball back to the screen. The main body of the example contains an infinite loop that waits, checks the bounce, and then moves the ball on the screen. Let's run the program to see how it works. Let's look again at the move function. It accesses the screen as a two-dimensional byte array in several places. So how are the accesses implemented? If we try to implement the access by using an index instruction of the microprocessor, we run into a problem. The maximum index value is 255. This is because the index register is an 8-bit register. So this approach does not work for large arrays such as the character screen. Fortunately, the microprocessor of the Commodore 64 supports also indirect indexing. Then we need to use a pointer register located on the 0 page of the main memory. This is done by loading a 16-bit address to the pointer register. Then that pointer register can be used to access the memory location indirectly. However, we run into a problem even in this case. Here, the row value is determined by a variable. Because of this, a multiplication has to be performed in runtime. Unfortunately, the microprocessor of the Commodore 64 does not support multiplication. Although we could implement the multiplication as a subroutine, this approach is too complicated for our use case. So the approach that is taken by the SHA-64 compiler is to pre-compute the row addresses for the byte array. Then we can load the row address to the pointer register by using an 8-bit index value. The column index can then be used together with the pointer register to access the value in the byte array. So with this approach, we can theoretically access any value in the whole memory of the Commodore 64. As for the compilation of the two-dimensional byte arrays, the parser and the binder are extended to recognize and support use of two indexes. That in itself required a substantial refactoring of the current implementation. So, to support a two-dimensional byte array, the intermediate representation language was also extended with a pointer register. If we look at the example source code, it gets translated to the following instructions in the intermediate representation language. There are now 3 new instructions for the use of a pointer register. One instruction is for loading an address value to the pointer register. Another instruction is for storing a value to the memory location indicated by the pointer register with an index value. And the last instruction is for loading a value from the indicated memory location. The intermediate representation is then used to generate the final bytecode. In this case, it looks like this by using the assembly language representation. By looking at the assembly code, it is clear that accessing a 2-dimensional byte array takes a performance hit. It is not, however, as bad as it looks. Let's run a program that fills the entire screen with characters 256 times. As you can see, it took about 16 seconds. So, by using the 2-dimensional byte arrays, we can fill the entire screen about 16 times in 1 second. That is not so bad. So that is what the 2-dimensional byte arrays look like. Next, I'll add variable declarations to functions. Until then, thanks for stopping by and see you soon!